Okay, so this is starting with the theory of where we're going with momentum and impulse. We're going to eventually look at like 2D collisions, and but you need some theory in behind it. So we look at the law of conservation of momentum. So you'll see here that it says in an isolated system. So once again, in physics, there are so many variables that we can't control. Like, unless we had millions of dollars of a lab at our disposal, we couldn't control it. So we always put it to an isolated system. And it says that the total momentum of all objects before an interaction is equal to the total momentum of all objects after the impact. Okay, so this is an isolated system, and this is what we're looking for. Total before equals total after, or this one here is what you're going to see. And so that epsilon sign means sum of. So if you had 5 objects before and 5 objects after, you would take the momentum of object 1, the momentum of object 2, object 3, object 4, object 5, and then add them all together, the sum of. Okay? So this is what's really important. Isolated system is defined when no net external forces act on the object or a collection of objects. Seriously.
Oh boy.
I'm not sure why. Is it frozen? No. So the words that we use, momentum, we talk about it in situations of collisions. So 2 objects coming into contact with each other, and not just, well, it could just be staying stationary, but usually there's a rebounding motion, okay, or an explosion. So the way that we do it is you need to make sure that you are doing your vector diagrams for each object before and after the collision. And I know you guys don't like doing it, but drawing pictures in this situation is really crucial to help you figure out where your information is coming from. So I hope you said it's okay that I erased this. That had all your sports up there or something?
Yeah, it's fine.
Okay.
I'm sure I'm not going to need it anyway.
So like if you had an object A here, and you had object B over here, and object A was moving to the east, and object B was moving to the west, this is your P before. And then you would draw a line, and you draw whatever happens after the collisions. So A goes this way, and B switches direction that way, or whichever, and then you would write P after. It's really important that you do this diagramming.
So could B still be
B
rolling?
could still be going there depending on the variables that we're going to look at, absolutely.
Alright.
Okay, but just to show you that there's a distinction between the two. And so you need to figure out the momentums. So you need to figure out momentum of A before, momentum of B before. You need to figure out momentum A after, momentum B after, or maybe you're looking for one of those components. But you see here that we have 4. We have A and B before and A and B after. Only one thing is going to be what we're looking for. Right? We'll have 3 knowns and 1 unknown. Okay? You add them up all before, you equal it to the sum of it after, and then you can solve for the unknown. So this is really important that we understand this Newton's third law. For every action we have an
opposite and equal reaction.
yeah.
Nice.
Okay? So that's kind of a little bit backwards to how it goes, but equal and opposite reaction. But you can say opposite and equal, that works too.
What's the, I don't know, I guess there.
You got it right though. Okay? So a collision between a large truck and a small car, both of them are going to have the same force because it's the same before and after, equal and opposite reaction. So a 250-gram toy car traveling east at 4.5 meters per second collides head-on with a 300-gram toy truck traveling west at 5 meters per second. After the collision, the 250-gram toy car is traveling west at 2 meters per second. What is the velocity? Paying attention that that's a vector quantity of the 300-gram toy truck after the collision. So if we start with our diagram first, what is not working here?
The smart part.
Well, besides the smart. Thanks, Jada. Jeez.
Funny.
So we have before.
Did you hit play on the iPad?
Did I what?
Never mind.
Okay. Okay, it says a 250-gram toy car traveling east at 4.5 meters per second collides head-on with a 300-gram toy truck. So this is before. So before we have a truck and a car, and they collide head-on. Okay? So you have the truck weighs 300 grams, and the car weighs 250 grams. And then it says after the collision, so you know that it's not starting from zero. An explosion starts from zero and then ends up with a velocity. That's something to keep in your mind. The 250-gram toy is traveling west. Well, I have these backwards. The car is going east. Make sure I'm paying attention. Car's going east. Truck's going west. And then afterwards, the car is traveling west, and the truck is traveling east. So here we see this one here. The car's velocity is 4.5 meters per second. And after, oops, let me draw another truck. After, or the truck is traveling 5.0 meters per second. Afterwards, the car is traveling west at 2.0 meters per second, and it wants to know the velocity over here. Okay? So what are the other knowns that we know besides the velocities?
Mass.
Masses. So we have mass,
Oh, you
mass of the car, mass of the truck equals 300 grams. And you what, Chris?
You gotta get those back in kilograms.
So what would they be?
0.25. And 0.3.
Okay, velocities. And so now the first thing that we need to do after we draw this is we need to calculate the momentums that we can calculate. And how do we figure out momentum?
Oh, it's like P equals mv.
P equals mv. So we have momentum of the car equals mass of the car times the velocity of the car. Momentum of the truck equals mass of the truck times the velocity of the truck. And this is before, so I'm going to put a little b there. Over here we have momentum of the car after. Okay. What's something else that we need to pay attention to, because it's asking us for a velocity which we know to be a vector quantity.
Need a direction.
We do need a direction, and how do we indicate direction without saying east or west?
Away.
Away.
And
What's
north.
a symbol? It's a symbol that I'm looking for you guys to say. How do we
Degree.
indicate what? How do we
Oh,
indicate?
no, wait a minute.
How do we indicate west, down, left? Yeah, but how do we indicate if something's moving left,
Never eat.
West.
body meters.
down? without using those words?
Direction.
What?
I'm so
Negative.
Oh.
A negative shows the opposite direction. The most basic mountain.
But I thought you were talking about words.
That was,
That's
I
why-
said with a symbol.
That's why I said degrees.
180 degrees from where we started at.
Yeah. There you go.
Yes, correct.
Okay.
Oh.
There we go. So, momentum of the car before equals what? How do we solve it?
1.125.
Okay, but how did you get that?
0.25 times 1.5.
Ooh, my smart board is really off. What did you get?
1.125.
And what are the units for momentum?
Kilograms and meters per second.
Ah, yes.
And how do we know that? Because mass is in kilograms and velocity is in meters per second. Whoa. What do you get for the truck?
1.5.
But don't forget the negative sign, right? What about after? Don't forget the negative sign because now the car is going left, right? What do we get?
0.5. Negative.
And of the truck,
Unknown. In the opposite
it's
direction.
not so much unknown. We can get that far, right? Now we need to remember that it's the total momentum before is conserved by the total momentum after.
So would you add the two to the left?
Yes.
Yeah.
Whoops.
And then we like to keep the negative in there.
Yes.
What?
So what do you get for the momentum before?
Negative 0.375.
Oops. And when you do the math on the right-hand side, it's not 1.5.
Huh, that's all it makes.
Okay, so the momentum after is 0.15 times the velocity of the truck after. And since that's what we're looking for, what do we get for a value? Ah, I did this wrong. This is not multiplied by. This is plus this momentum. Sorry, that's my bad. So when we get negative 0.375 plus 0.5, what do we get for a value? Yes, remember I just said I did it wrong. Well, I multiplied it instead of over here, Jaden. It should be the sum of, right? Which is the momentum of the car plus, and I had multiplied it.
Isn't one negative though?
This one here is negative, and when I bring it over to this side, it becomes positive,
Oh.
right? I have to add 0.5 on this side to get rid of it.
I got her.
Okay. So what do we get for a value?
0.125.
So 0.125 divided by 0.3.
0.416.
Okay. Which gives us our final answer of, when we look back, we have 250, 4.5, 300, 5.0, 250, and 2.0.
0.42 meters per
Thank you. But it asked us for velocity, so what's the other piece of information?
second.
The direction.
Yeah.
Right, and we're looking at it from the truck.
At 180.
Because this answer here is positive, right?
I just saw the diagram. Truck's going that way.
Well, because I drew the diagram that way, but if you didn't know, because potentially the truck could still be going that way. If its mass was substantially larger, then its momentum would be substantially larger, so it would keep going in that
But
direction.
it wasn't.
Hmm?
Okay.
We'll investigate that. They lost all 7 games.
7 games.
Yeah.
They gave it their all though.
They did. When they followed what Mr. Spence wanted them to do, they did not bad. A satellite starts to drift. Cameron, I'm recording, so I'll upload it and you'll be able to. Okay. A satellite starts to drift off course. The path of the satellite is corrected by the engine thrusters expelling some gas. The expulsion, which is another code word for explosion, of 65 kilograms of gas increases the speed of the satellite by 7.5 meters per second. If the average exit speed of the gas is 118 meters per second, what is the mass of the satellite? So what we're looking at here is that we have a satellite that has engine thrusters in it. So here's our satellite, and here's our engine thrusters inside of it. Okay? It's got like gas tanks or like oxygen tanks inside of it. Okay? Fuel tanks, that's the word I'm looking for. The expulsion of 65 kilograms of gas increases the speed of the satellite by 0.75 meters per second. So what we see is this is our before, and then our after looks like the satellite going in one direction and the thrusters going in another direction. Okay? Because the force of them pushing away is going to send the satellite. So we're just going to arbitrarily pick them doing this. Nothing in there that says one goes east and one goes west. So what do we notice about this before satellite with the engine thrusters? What can we not assume about? What knowledge could we have about that?
We have the gas weighing 65 kilograms.
Yep.
And then it's speeded up to 7.5 meters per second.
Yep. We're going to get there. But what do we notice about this diagram?
It must be
I like that.
I was kind of hoping for a reprieve, but okay. It's 1 unit, right? And the momentum, we learned this, the momentum is P1 plus P2 and however other many momentums there are. So this is 1 unit, the satellite with the engine thrusters on it.
Because the gas is still inside.
Because, yeah, it hasn't, the thrusters haven't been engaged. So our mass is going to be equal to mass 1 plus mass 2. It's 1 unit. Okay? So our mass is equal to the mass of the satellite plus the 65 kilograms that Jaden pointed out. So we have our unknown variable, mass of the satellite is right here. Afterwards, here's our satellite and here's our thrusters. So we have mass is unknown. And then our velocity, I'm going to show you another symbol. Instead of writing VB for velocity before and VA for velocity after, I'm going to use the prime symbol. Have you guys been taught that? Prime? Okay. So prime means it's our second velocity. So this is velocity 1 prime is equal to, this increases the speed of the satellite by 7.5. And V2 prime says exit speed of the gas is 118. Okay? Make sense? What's our initial velocity? It's not unknown. Expulsion is code word for explosion. So what? 0. The velocity before an explosion is 0.
Yeah, but like in space, it wouldn't just stay still. It would move because there'd be an orbit, so
That's
it'd be
easy.
going.
That's what?
But the other thrusters are going to keep them on spot.
But then it's still velocity.
It is. We're going to assume it's 0. Remember? Because we're in an isolated system.
That has an orbit. That's good.
Life is good. So it doesn't matter. Momentum before is mass times velocity. It doesn't matter that we have this unknown variable because anything times 0 is 0. Okay, afterwards we have this. We have P1 prime is going to be equal to M1 prime V1. Actually, mass doesn't change.
I'll stop the video for you.